This is one of those amazing days. So it's a pleasure to have Senya Shlosman from Skolkovo ITTP and BIMSA, visiting BIMSA, who's going to talk about KPZ scaling and the Tracy-Widom distribution in the Ising model.
Hopefully I share with many of those people who are sitting here in that audience. So I was working in studies on the Ising model for many years, and I looked on it as some. There are too many advices I hear at the same time. So what should I do? You will see very soon. Very soon. I will tell you about 1 dimension and about 2 dimensions, and my main topic would be 3D. This is definitely the case. Хорошо слышно или плохо слышно? Что я должен сделать? Я не понимаю. So I don't know. So tell me what to do, and I will do whatever you tell me. Good. So I will start, and you will see that this Ising model, it has a look of something quite simple and elementary, so you don't expect much of it. But still, as time went, I was surprised to see more and more striking questions about it. And what I'm going to tell you is about the connection between Ising model, which I consider to be something pedestrian, and this Tracy-Widom distribution, which I consider to be quite sophisticated object. So I was very surprised to find out that there is a very close, there is some connection between the two. So this is what I want to explain today. So the Ising model was, I participated in a celebration of 100 years old, when the model was 100 years old. It happened exactly when it turned 102 because of the COVID. So the conference, the memorial conference in Bure-sur-Yvette was postponed twice. So it was already a few years ago when it happened. So the model is quite old and well known. And so Ernst Ising was a student of Professor Lenz. So he solved the Ising model in 1-dimensional case, found there is nothing special happening there. And that seems that that's his main contribution to the theory of the Ising model. But so here you see him, that's Professor Ernst Ising, and here you see a 2-dimensional simulation of him. So he's became by studying this model, he made himself very known person. So people do many things in his memory. So that's his picture. So I will talk. What I will be interested most is about 3-dimensional Ising model. But on that definition that you see here, the dimension doesn't matter. So we take a lattice. Here it is 3-dimensional lattice. And on every side, we put a plus minus variable. At every vertex of the lattice, in finite volume V, we put a plus or minus 1 spin. Those variables are called spins. And then to every configuration, sigma sub V, we correspond an energy function. What is it? We take all bonds inside V. X twiddle Y means that X and Y are nearest neighbors in V on that lattice ZD. And then we take a product of sigma X, sigma Y, those are plus minus 1s. And we sum over all bonds and we put a minus sign. And this is the energy of the configuration of those plus minus spins in the box V. Okay, and then once we assign to every configuration a number, this H of V, then we form a probability distribution on the set of all such configurations by this formula which you see at the bottom. So you take exponent of minus H of V. So see again, you have minus there and minus again minus here. That's the tradition, the physical tradition. And then you put a numerical factor, minus beta, that's a real number. The beta inverse has the physical meaning of temperature. And then we make this array of numbers into a probability distribution by normalizing by this factor Z, which is called partition function. X with Y means that the X and Y are nearest neighbors on the lattice, right? Okay, so that's it. That's the definition of the main object of the Ising model. So indeed, you see that on that one slide, you have almost all definitions needed to try to start to study this. And you see that this is not something too complicated. Yet, very great minds were working on that probability distribution and its questions related to that. So here are a few pictures. So this is Bendelin Werner. This is Stanislav Smirnov. And this is Hugo Dominil-Copin. Those three people got the Fields Medal quite recently. And all of them were doing research, and the main part of their research was to Ising model or Ising model related questions. So indeed, this is quite an interesting field. And as I told you, it is not exhausted by during the 100 years, 100 years old that it is. Okay, so that's again the definition of this probability distribution. Let me do a little bit more to formulate the question that I want to address. And it goes as follows. So what we do, we slightly change this energy function. The value of energy we assign to every configuration in the box V. What we do, we take a box V and we also put some spins outside that box on the exterior boundary of that box. Okay, this is a parameter. We fix this configuration outside. It is called sigma bar. And then we write down that same formula before. And the first sum is indeed, again, the sum over x and y's, x's and y's inside the box, which are nearest neighbors. And then we add an extra term where, again, x and y are nearest neighbors, but x is inside and y is outside V. So just a distance one, but outside. So that's boundary condition. And then we again do the same. We write down the same probability distribution, which is called Gibbs probability distribution, if I didn't say it. Say it again. Outside means outside V. Yeah, I have a box V. V is a finite box. V is a finite box as it was before. Yes, and then it is a subset of a lattice. So there are points which are inside V and there are points outside V. So in particular, there are some points in V such that their neighbors are outside V. Those are the points. Those are the points which you see here. See here, X is sitting inside V, Y is sitting outside V, yet they are nearest neighbors. That's what I'm talking about here. So we have this boundary. Say it again. Edge effects. For me, my box V is a subset of a lattice. So that I'm not concerned with edges. My V is set of bonds, set of sides. Is there a choke here somewhere? Yes. So this is my V. This is the boundary of V, if you wish. Those are points outside V. So there are no edges on the boundary. So the terms I'm talking about here, X with Y, X is in V, Y is outside V, are those pairs. This is X and this is Y. And so this second sum is over bonds which look like this. The first sum is over bonds which are like that. So that's what I mean by those definitions. Okay, so this is slight modification. So again, I have probability distribution on the configurations in the box V, but now this probability distribution is somewhat affected by what I put outside. Just minor change to make life more interesting. Okay, and then in particular, what I can do, I can put outside all pluses, and I can put outside all minuses. Then I just fix those outside parameters to be all pluses or minuses, and then I repeat again the same thing. And what I would get, let me denote specifically by those two probability distributions which correspond to all pluses outside and all minuses outside. Let me denote them by mu plus and mu minus. So this is again the same definition, but with the outside boundary condition prescribed. Very good. So the non-triviality of the Ising model is that the questions you are asking, you want to ask them for all boxes and even for boxes when you go to infinity. So this is why the non-triviality comes from that infinity which is there. If you would do it on finite boxes, then nothing interesting you will not see anything interesting. So the interesting cases, the interesting questions arise as you take your box infinite. In my setting, you need to take this box V to be infinite. And once the model becomes infinite, you understand that that's the source of all complications and interesting points. That's it is this secret which makes it non-trivial. Okay. Say it again.
The order of the transition.
First order. Sorry, I'm sorry. So in temperature, the second order. It's second order in all dimensions. Okay. Okay. And so the interesting thing which happens here is this one. It is on the screen. So you take this limit as your box goes to infinity, and you find that those two probability distributions, they go to limits as your box goes to infinity. But whether or not those two limits are the same depends on your parameter of the temperature. So when the temperature is high enough, when beta is small, when beta is less than or equal to some critical value, then the two limits are this one and the same measure. And once your temperature is lower than the critical temperature, the two states are different states. The two probability distribution, the two sequences of probability distribution, they go to different limits, mu plus beta and mu minus beta. And this is what was what made the Ising model very famous and nice, because that feature indeed models the behavior of the ferromagnet. Ferromagnets, they have some long-range memory between the different parts, but only when the temperature is not too high. When the temperature is very high, your magnet loses all magnetic properties, but when temperature is low, you have spontaneous magnetization. So this is why the compass is working at room temperatures, because there is this spontaneous magnetization. In mathematical terms, this is this inequality that it has magnetized states, and they are different probability distribution. They look different. Okay, and so we'll stay in this region of temperatures, low enough temperature, below the critical temperature, and we want to see what is going to happen there. So as you see, we have two phases. One is this one is called positively magnetized. This one is called negatively magnetized. The positively magnetized looks like that. It looks like a sea of pluses, and then there are islands of minuses there. Maybe inside again. So that's how the plus phase looks. The typical configuration taken from the probability distribution looks like that. And if you talk about the minus phase, it's just the opposite. It's sea of minuses with islands of pluses there. Okay, the next thing we want to do is to put the two, we want to arrange our system in such a way that it will have two phases at the same time. We want to condition it in such a way that that the box would have plus phase somewhere and minus phase somewhere else. And what we do is what is written here. We have the probability distribution on all configuration of sigma x, but now we want to condition this. We want to consider this conditional distribution. This is a conditional distribution. So we take the minus state, but we want to consider only configurations which have prescribed magnetization. This sum is called magnetization. And for example, I take, say, is written here, I put my parameter m to be, say, -1/2. Then what has to happen is that we will have some part of our box, a quarter of that should be filled with the plus phase, and the remaining 3/4 would be filled by the minus phase. It turns out that the piece of plus phase would not be spread over all box. Like if you have droplets of quicksilver on the table, they tend to merge together. So this is indeed what happens here. That's a theorem here. So this region of plus phase that we put inside our system by force actually merge together, and it is a large droplet, random droplet, and of sizable size. And we want to say something about how that droplet behaves. And it turns out that it has an asymptotic shape. So it looks like some deterministic shape, which is, this shape is obtained as a solution to some variational problem, which I will tell you a little bit later. And so we wrote a book with Roland Dobrushin and Roman Tatetsky about two-dimensional case, and later there was the three-dimensional case was also treated later. I will not talk much about that. So this is how a droplet of plus phase inside minus phase look like. This is the asymptotic shape of that droplet. So if you have a portion of your box, if you want to have minus spins and plus spins at the same time in your box, then those extra pluses, they would merge together, and they will have some. They will make a big droplet, random, but this random droplet has typical shape. If you scale down the fluctuations, if you scale your n by n by n box down to n, down to 1 by factor n in all three directions, then this random droplet would still be randomly located there inside, but the shape will not be, you will not see any more randomness. It will just a deterministic shape. And you can find out what is this surface. You should solve some variational problem. And this is, and what you see would look like a dice. Namely, for the Ising model, it will have six flat facets. And then it will also have some, and then the edges would be smoothed out, and the vertices would also be smoothed out. So it's really like a dice. This is what you would, that's a theorem. This is how the droplet of one phase looks like in the three-dimensional case. So this, let me say it again. So this random droplet has a non-random asymptotic shape. Once you scale it down, the local fluctuations would disappear. They are of smaller order than linear. And so you will see a deterministic shape. This is the shape that you would look at. And here is some pictures you can find. So this is how the real crystals are looking. So this, what I showed you, people call Ising crystal. And this is, and those are true crystals. Those are droplets of lead. So as you see, it has a facet here, and then a rounded part starts here. So this is this top monolayer, and then you have the next one, and so on. And this is a rounded part. So this is the region that we will be interested in studying in our in my talk. Okay, so good. So this is exactly what I want to study, how this droplet, what's the geometry of that. And now I go to random matrices, which in a sense provides an answer to some of the questions I'm going to discuss. So this is a creator of this branch of math, Eugen Wigner, a Nobel Prize winner in physics. And he was studying the spectrum, the energy spectrum of heavy atoms, and he was interested in knowing how the distribution of the eigenvalues of energy levels, to say something about the energy levels of those big atoms, and he came with the idea, with the feeling that the spacing between the lines, the energy lines, should look like a spectrum of large random matrices. That was his idea, and that is why he was studying random matrices. So what is random matrix? Random matrix theory. Well, the simplest case is, and the one that we will need is this one. You take n by n matrix, and you fill this table with independent Gaussian random variables. And you want your matrix to be Hermitian, so you just fill the upper half of your matrix by independent random values, independent identically distributed Gaussian complex. Then on diagonal you put real Gaussians, as it should be for the Hermitian matrix. Okay, and then that's your object. You see the probability theory. The simplest thing you do when you study probability theory, you want to know what are how the sums of independent random variables behave. And here's another thing, another occupation for probabilist. Again, you have a huge array of independent random variables, but this time you made them into a matrix. You get a random matrix. Matrix has a spectrum. So that spectrum then is again a random variable. It's a function of all those random variables that you choose. And you ask yourself how those random variables depend. Of course, that's a bit harder than just studying sums of independent random variables, but people do this and see you start with Gaussian because that's the easiest thing you can do computations. In particular, you want to know how the largest eigenvalue behaves. So you know the distribution of all those x's. You take your matrix, you compute the leading eigenvalue. It's a random variable, so it has some fluctuations. You don't the first thing people say, which inside probability, the first thing you expect, okay, should be Gaussian. Everything should be Gaussian, but that's not in that case, of course. So you do this, you compute this random function of your x's, and that is a random function. That's a random variable which has some distribution. And this is famous distribution called Tracy-Widom distribution. And you see its definition here. So what you should do, you take your random number, this leading eigenvalue, lambda maximal. You first make a shift. If your matrix is n by n, then you subtract square root of 2n. And then you multiply it by n to 1/6. So this is thing unheard in classical probability theory. You don't do such things there. But here is what you need to do in order to have some meaningful limit. So this is a quite non-standard normalization. But if you want to have something which has non-trivial limit, not uniform and not just a delta function, this is how you should normalize it. And once you do this, then you get some proper, normally looking distribution. And that's the distribution one finds if one do what I say, and then you take a limit as the size of your matrix goes to infinity. And this distribution we are going to see in the Ising model. Next thing will be where to look in the Ising model in order to see this. This I will tell. Sorry?
Is there a scale?
Explains what? Explains. Sure there is. Sure there is. I will not say you a word about that. I will explain other exponents. I will not explain this one. Okay. So let's go back to the Ising model. Now that I told you the answer, which will appear later. But now let me tell you a question to which that is an answer. So as I told you, we want to study this crystal, the Ising crystal of one phase in the other phase. And now we want to build it layer by layer. So what I mean by this, let me maybe show you a picture here. So what we'll do is the following. We take a cubic box in the three-dimensional space, and we put plus boundary conditions in the lower half, and we put minus boundary conditions in the upper half. And then inside we have some configuration. If the temperature is low, then in upper half, what we will see would be a minus phase, and in the lower half, we will see a plus phase, and we will see a random interface between the two. But it will be more or less flat interface. It will not fluctuate much, no matter what the size of it is. But then we want to to see that droplet that we are interested in. So we condition our system by having more classes than just one half as it is here. We say we condition it, and we put by hands more classes. Then that surface should probably go somewhat up. And then by adding more and more, it will be higher and higher. And this is the way we will study. We will see how much. And finally, it will be this crystal, this big one. But we want to see a process of building it. So what we do here is this. We have this, our system with this plus minus boundary condition. This is PM means that in the lower half we have pluses, in the upper half we have minuses, same formula. So see, in the lower half we put here a plus sign. So those x's are close at the boundary, but inside our V, but in the lower half. And therefore, the nearby spins are plus ones. We don't write them. So it's just sum over all x's inside the box on the lower half. And then we have minus sign for the spins above. And we take that same probability distribution, which appears fourth or fifth time here. That's the Gibbs distribution in that box with those specific boundary conditions, which force the interface inside. And the last line tells us that we want to have more pluses than minuses. So the meaningful question is to study this probability distribution on the condition that the total sum of all pluses and all minuses is of the order of a times n squared. If the constant a is 0, that means we have half plus and half minuses. So that's the initial thing. And then we add more pluses. And more pluses means that there is some force which pushes this interface upwards. And we want to see what would happen as a grows. Very good. So beta is fixed positive number, but below the critical temperature. And in fact, for the technical reasons, we need it to be small. But that's where the proof works. But it's the inverse of temperatures. So large beta means small temperature. Yes. So we have two phases. Right. No, on the boundary, everything is fixed. Half is pluses, minuses. The bottom half is plus. That is kept fixed. But inside the box, we say that we want a little bit more pluses than minuses. And a little bit more means a by a n squared. And we want to see what will happen when a would increase. You will see, you will now see exactly what. This is the list of papers we did on this with late Dima. So he was a very important contributor to these studies. And so again, this is our boundary condition. This is this interface which is forced inside by the boundary conditions. And what we do now is let us position ourselves here on the top there. So I will now sit there and I will look on this interface from the top. So I will see something squared, and then on it something is growing. And I make my eye in such a way that I don't see small things. I only see things of size of n, of the order of n. Okay, and I have this parameter a, and I'm telling you what I will see if as a would increase. And so the first news is this. I will see nothing. It's a square, and nothing interesting is in there. Before this constant a is less than some threshold value. It's just a flat interface with some small things going on, growing it up and down. Nothing else. It just stays flat. Yeah, sure. Here, this is extra number of pluses. So when a is 0, you have equal amount. When a is large, you have some more. And as you will see, this a really is indeed controlling something interesting. But for a less than some fixed value, nothing interesting happens. And you just see a void table. Nothing. Say it again. So this interface, well, in a sense, it is rigid, but in another sense, it is not. Not means that there are some small fluctuations of it up and down. If a is positive, then maybe you have more ups than downs. But they are of size logarithmic in n, so they are there, but we don't care about them. We want to see grand. We want to look grand, big. Okay, and so till some threshold value of A1, you see nothing. A1 depends on temperature and details of interaction. You see nothing. Good. And then you pass to the threshold A1, and then you see something. You see a monolayer of plus particles suddenly pops up. So here, the height is 0. It's just that flat part. And here, inside, this height is 1. So just one monolayer of atoms pops up. So because of the pressure from below. And that's how this random interface reacts to that. So you see suddenly a big random thing of the size of the whole system. It's not that size. Well, that size grows as A grows, but it doesn't go to 0. You either see something quite big, or you see nothing at all. So that's how that first transition happens. All of a sudden, you see some large object, random, and it sits somewhere inside your square. And then you increase your A further, and it grows. This monolayer grows. And then you increase it still further, and it grows more. There are walls. They does not allow it to grow outside, so it grows like this. And then you go still further. And what you see that the outer, at a certain moment, the outer contour shrinks back a bit, and inside the second one appears. So here we have height 0, here is height 1, and inside there it's height 2. So it's a cake with 2 layers. And that picture goes on. So then the inner one grows, the upper one shrinks, they meet, then they grow together. Again, the walls are there, they do not allow it to grow further. And then at a certain moment, a third one appears. So that those two go back a little bit, and the third one appears somewhere inside. And this is how this evolution goes on. Okay. That's exactly theorems. Those, what I'm telling you are theorems. Right. So you can say how those curves are looking. I will tell you a little bit about it. It's much more than calculating partition function. You need to know the random geometry of this object. But in particular, you have to have a very precise control of various partition functions, which you do. I telling the results, of course. Yes. It's nothing funny here. Indeed, the calculation of partition functions is the main thing here, which I am not telling a word about, because you don't want to know this today. But you really, what you do is use of so-called cluster expansion. There is a technique of cluster expansion which allow you to treat partition functions with very precise technique. So this is what all that is based on. Say it again.
Then either an experiment can control the spin outside the plus minus boundary or you can keep it.
What that has to do with the reality, maybe. So there was these pictures I was showing you, this crystal. Okay, so once the crystal is there, you just take part of it, and that's it. That's exactly what I'm talking about. If you cut a piece around this interface, then you see that you have those layers and you have the walls. So it is just so you can observe experimentally those features, just cutting out a small piece of your crystal. Okay, so good. So we want to study this. So let me tell you a little bit about just first line there. So there are more and more lines. So the more lines are there, the harder is the discussion. So let me tell you about just one single line. But the single line, for that, you don't need actually to go to 3 dimensions. You can have such a situation already in 2-dimensional Ising model. You have a phase, a minus phase, and inside you have a big plus droplet. So this is, if you just want to do this, then there is no need to go to 3 dimensions, but we will go, but not at that moment of just one layer. How I am doing with time, by the way? 2-3 minutes. Make it 5. Okay, so we studied this question with Roberto Schoenmann some years ago, and this is what we found. So if you prepare your 2-dimensional Ising model appropriately, that is, you put minus boundary condition outside and you put inside small plus magnetic field, then you will create a droplet like the one I was telling you about, and it will have this asymptotic shape, like the one we wanted. But it's and let me show this to you. That's the true simulation now, and this is the picture that you will see in 2-dimensional Ising model. You have a question? I have it. Yeah, I have a minus sign in my Hamiltonian. It's ferromagnetic. Only ferromagnetic. I have minus the sum of products of it is ferromagnetic system. Yeah. Right. And see here I have minus boundary condition, those are yellow, and I have small positive magnetic field, and it forces a droplet inside. But because the field is very small, so the corners here actually are not affected by this plug of magnetic field. So you still have some region of macroscopic region of minuses here, but the bulk, so the asymptotic shape of this is this one. So here is minus boundary condition, here is minus phase, and here is simply plus phase. And okay, and then we see this random line. So the question is how that one behaves. And it is this one which has this, and so the interesting good news is the following. So if this is a box of size n by n, then the fluctuations of this interface is n to 1/3. It is this exponent which this is a modern exponent, 1/3 exponent. So 1/2 is what you do in Gaussian and independent random variables, but here you have the fluctuations are 1/3. And when you so this is where we. So last year we published the paper was published by Annals of Probability, but by late Dima Yoffe, Sebastian Ott, and Ivan Velenik. So this is about the behavior of that line. And the answer are the following. So see, we do this KPZ scaling. So that's where the word KPZ in my title appears. So you have this object, and then you should, this random line, you scale it by a factor 1/3 this way, by a factor 2/3 that way, this random line. After that, what you see is some proper random process. It has finite fluctuations, everything like that. And you can compute things about that process. And in particular, it is governed by something which is Airy function. Airy function appears here as what describes that process. And let me, so this is the Airy function. Airy function is something everyone should know. And this is the case, right? See, everyone knows. So, and that's the graph of the Airy function. It's very important function. And that's its graph. So So what you should do in order to use it in our model, you should just move the origin to its first zero. Then you take this thing here, and the last thing what you see, you square, right? And this squared shifted Airy function is exactly the distribution of the height of this interface. So in the big box of size n by n, it fluctuates like cubic root of n, and if you scale it by n to 1/3, it then will become a random variable. Right. And it has a distribution now. So, and this is the distribution. You take your Airy function and you square it. That's the answer. Okay, and the Airy function is here. You take this second order operator minus second derivative plus x. That's a differential operator of second order, and you put zero Dirichlet boundary condition at the origin, and then we look for eigenfunctions. And this shifted Airy function is the leading eigenfunction. This is what governs this random thing. Very good. Now let's go to several layers. So let us take k layers, and then believe me, instead of this one-dimensional operator, you have to consider n-dimensional operator, but very simple. This is second derivative of x1 plus x1 and so on. You just take a sum of them. They are, so to say, not interactive. And then you also need to know the eigenfunction of this operator. It's very simple if you, but you accept that you need to know a box in which you do it. So the simplest box is just you take here are the other eigenfunctions of this. So and here you see, I believe the second eigenfunction looks like that. You just shift your Airy function to the second zero and so on. Those are all the eigenfunctions of this operator. And those are entering to the question of what are the eigenfunctions for this multidimensional sum. So there are two cases when you can write down easily what are those eigenfunctions. The first one is you just take the positive ortant, so a product of positive semilines, and there you just that's very simple. You just multiply eigenfunctions of a single one, of a single operator, and that is an eigenfunction of your operator, and the eigenvalue is sum of those eigenvalues for those. In particular, the main eigenfunction would be just the product of Airy functions. Okay, and then there is another case which is important to us. It is the case when you are trying to solve the Dirichlet problem in this chamber. There you also can write down the eigenfunctions. But now you should work, and then what you have to do, you take n different eigenfunctions, and you form a determinant, the Slater determinant. Here it is. So you take, if you want, so you need the functions of n variables. So xj are those variables from x1 to xn. And then you take all your n functions, phi, eigenfunctions, and then you form such a determinant. And this determinant is an eigenfunction. Those determinants, depending on which function, different eigenfunctions you put in, are all eigenfunctions of this one. And the leading eigenfunction would be if you just take the first n eigenfunctions of the operator, of this one-dimensional operator, and this is that's the object you need. So you take first eigenfunctions of this Sturm-Liouville operator, you make a Slater determinant, and that n-dimensional probability distribution with this density. Again, you see you have not the single function, but this determinant square. That is the density of your probability distribution n-dimension. So we have a formula for this situation where we have n lines here. So those are these n lines. Okay, so the final thing is very easy. One has to go to limit. You take this Slater determinant of eigenfunctions of this operator, and you take a limit as f goes to infinity, the number of layers. Okay, and this is what we did with Patrick Ferrari. It is published in this year in Journal of Physics. So the top line has some distribution, and you can write explicitly because there is this formula from the Slater, and you know those eigenfunctions. This Airy function is well known. You know all the asymptotics you need, and it indeed goes to the Tracy-Widom distribution that I told you about. So I told you everything except I didn't show you the cylinder from which I took this cat, how that cylinder looks inside. But this I would be unable to. So that's it.
Okay, questions? So I feel like I didn't understand something very fundamental about this. How is this probability distribution? So you said that if I let this cube have large size up to infinity, then as temperature increases or decreases, I have two only phases. So
not temperature decreases. At every temperature,
at
every low
temperature,
temperature, you have two phases. Right.
The question is, I mean, from the formulation, this is basically just telling me if the temperature is very low,
Right.
then my probability measure is only depending on, it doesn't depend actually on anything that on my configuration, initial configuration.
I don't know. It did not
When
just
the temperature is high,
when the temperature is high, it is the case. When the temperature is infinite, you have they are independent. The lower the temperature, the more they are interacting, and the attraction that is built into the system is there. So at low temperature, it is attraction, and it is there, and that's why this phenomenon happens.
But then how do you make a choice of, because for instance, that picture that you draw over there, that is basically, if the temperature is very high, your measurement of probability is just, but it doesn't depend on whatever you start with.
But at high temperature, you don't see this.
Okay.
There is no plus phase, there is no minus phase. No matter what you put outside, you have just Bernoulli independent random variable, so to say. Dependence is very weak. So this is a picture at low temperatures. You say you put all pluses, and then below that, not very low, below the critical temperature, you put all pluses, and then the system inside remembers this, notwithstanding the distance, notwithstanding the size of your box. Once the dimension is 2 or higher, that will be the picture, and it will stay like that in the limit.
I see.
So that's
maybe another quick question. When you start from this cube, if I make the cube very thin but very, very wide, what happens?
That's a legitimate question, but see, you should not do it in such a way that it will not becomes uninteresting. If this size is not growing, then there is just no space there. So you put more particles.
See how much symmetry actually kind of influences this. I can break the symmetry of initial configuration in many different ways.
You mean?
But then if I increase the large to infinity,
you just the base to infinity and this. Well, symmetry. Okay. That it was a cube and not a rectangle is of no importance. Why there is a size that where it get if the number of layers that you can put in can go to infinity as the size goes, then everything is
the same. If you make it very thin,
and if you make it very thin, after a few steps, you get
it affects the boundary things, because on both sides everything will have more boundary.
if your box Which question? So you should be a friend, not somebody who is making questions more precise.
I'm a very honest friend. So, what if this height is
The height of the box.
the height of the box is of the order of the correlation length of the Ising model?
Correlation length is it is a constant. Your correlation,
No. You have a bulk. In the bulk, you have a correlation length.
right?
The way how exponentially
But
decay.
the correlation did not decay in the sense. So you have long range order. Your correlations do not decay. You have plus phase below the critical temperature.
Correlation functions they decay exponentially.
No, truncated correlation function decay. But the true correlation function, they not decay. Sigma x, sigma 0, sigma x does not go to.
I'm talking about truncated.
Okay, and then it's exponentially small. It has nothing to do with that.
But what if your height is of the order of the?
Okay, so that it means finite, right? I'm at fixed temperature, so it is finite.
No,
then,
it's okay. Anyway.
No, so it's the same question. What happens if it is finite?
It's a very long.
The answer is very simple. No.
I'm talking about below critical temperature.
So below the critical temperature, the following happens. This is your.
It's irrelevant.
This is your box.
Sorry.
Okay, this is your box. So what will happen is your surface would hit this wall and would stay there. That's it.
I have a question of a friend.
Good.
Okay. So can you go back to the droplets?
Well, stop me once you.
Yes, go back. More.
You want to the red droplet?
More. Oh. Here. So what if the concentration of whatever is inside of this droplet is small, so that this droplet will not touch the walls? It will sort of sit.
Right.
Your condition will be such that it will be small enough to be inside.
You can cook up a question to which the answer would be like that, right? You can do that.
So what is known about this?
It's known the following. So, okay, in 3 sentences. So there is this variational problem which you should solve here. The variational problem has a solution of a nice round thing, square, so to say, but rounded and smooth. Okay. So in case you're asking me, you will see a droplet of that shape, but it will fluctuate around it. So the shape will be, in a sense, non-random, but the location is random. Because there are no walls, it can go wherever you want. It doesn't want to go to the walls because there is no. You want to fluctuate.
So right? It's a uniform distribution of these droplets.
Right, absolutely. Okay. It's uniform distributed there till you grow it so much that it cannot fit in. Then what happens is that then the shape would be different. So if once you hit the walls, then there is.
Okay, I understand.
4 segments here, straight segments. It is just like this.
Yeah.
And here you have this random thing. And it is here that you see this n to 1/3 fluctuations near the wall.
And I'm afraid to.
Don't be afraid.
Okay, let's thank Senya again.
Thank you. Thank you.